Welcome to Chapter 4. In 4.1, our objective is to evaluate indefinite integrals. Indefinite integrals, or antiderivatives as they are also called. Please try to think of these as synonyms. Antiderivative. If you break this word down, we know the word derivative. We've been doing derivatives now for quite a while in calculus, but now we're taking a prefix to it, anti. Antiderivative, not the derivative, opposite of the derivative. Think of it like this. I say, here's a function, y equals x squared. Let's say that this function is the derivative of another function. So instead of y, I'm going to call this f prime to indicate this is the derivative of another function. What could that function have been? You think to yourself, well, what did I have to do to get this to be the derivative? So I think I had to subtract 1 from the exponent after I multiplied by the exponent. So I think it could have been x cubed, but I had to multiply by that exponent. So I had to get the 3 to go into the front, but the 3 isn't here. The 3 can cancel out if this had a 1/3 over here, so that I'm left with just a 1 after I multiply by a 3. But lots of difficulty in just thinking backwards, so we're going to go through the rules of thinking backwards. But that's what an antiderivative is, thinking backwards from the derivative. Backwards from the derivative. So we're going to define capital F, we're going to use the symbol capital F as an antiderivative of little f on an interval if capital F prime of x, so the derivative of the antiderivative, equals little f of x. And to be more specific, we're going to say only for all of the x in I, that interval that was described earlier. A general antiderivative, so we're going to say capital G to name this general antiderivative of f, if and only if capital G of x equals the antiderivative plus some constant, plus c. C is called the constant of integration. Why is there a constant of integration? Well, let's think back to that first example I gave you. So again, let's say f prime could be x squared. What would f possibly have been? Well, we said f could be 1/3 x cubed because I multiply by the 3, I get 1 as a coefficient, I subtract 1 from the exponent, I get 2 as the new exponent. But couldn't f have been 1/3 x cubed plus 5? Because I take the derivative of that and I get 0. Couldn't it have been plus 5 pi? Because I take the derivative of that and I get 0. Could it have been plus or even minus 5 pi times 100? No matter what I put here that's a constant, add it or subtract it, the derivative of that constant is 0. So when we take antiderivatives, we have to keep in mind that there is a possible constant in the original function because the derivative of a constant is always 0. So anytime we do an antiderivative, we say the function plus a constant, c for any constant, and we call that the constant of integration. Now, a lot of times we write the derivative as dy dx instead of f prime. So I want you to look at it like this. Let's say dy dx equals the function f of x. Let's do a little bit of balancing in the equation so you can see where some of the notation comes from. I'm going to multiply by dx on both sides to this equation. Then I get dy equals f of x times dx. Then I'm going to use integration, an indefinite integral, to show the antiderivative. Remember we said these are synonyms, the antiderivative and the indefinite integral. So I'm going to show taking the indefinite integral, or this is called the antiderivative of dy, but I do it to both sides of the equation. The antiderivative, or the integral of dy, the derivative of y, go backwards, you get y. Not the derivative of y, you get y. The antiderivative, or the integral of f of x dx, go backwards, and you get capital F of x, the antiderivative of f of x, plus some constant of integration. So I'm going to define some of these parts for you. First of all, this equation we started with that had a derivative in it, because it has a derivative in it, it is called a differential equation. It is an equation that contains a derivative, so it is called a differential equation. The symbol that we use for doing the antiderivative is an integral symbol. This is called the integral symbol. The function for which we are taking the integral, or the antiderivative, is called the integrand. The dx is called the variable of integration. The way we describe all of this part over here, or the integral of f of x dx, is we say the antiderivative of f of x with respect to x, the antiderivative of f of x with respect to x. So we're going to go through some rules or formulas for doing antiderivatives, but these you can figure out because you know derivatives, you just have to think backwards. So for example, the antiderivative, or the integral of 0 with respect to x. Well, what function has a derivative of 0? A constant function does. So the integral of 0 with respect to x is c. That's our constant rule. For example, if I say, let's do the integral of 5 with respect to x. Nope, that's not 0. That's a 5. That's a 5. That example is going to go for the next one. The next one is doing an antiderivative, or an integral of any constant dx. That's the one where we're going to say, what's the antiderivative of 5 with respect to x? This one is just 0. We're not replacing any constant in there but 0. So ask ourselves, what's the antiderivative, or what function would I take the derivative of to get k? Or in this case, what function would I take the derivative of to get 5? I would take the derivative of 5 times x. But remember, we are always adding that constant of integration. So here's our rule. The integral of the constant is the constant times x, always plus a constant of integration. If I'm multiplying a constant times a function, that works just the same as like when I take a derivative. Pull out the constant, multiple, and then do the antiderivative of the function with respect to x. Now to our power rule. Think about how we do a derivative. If I say the function is x to the 5th, and I do the derivative, dy dx. Think of the process. I multiply by 5, and I subtract 1 from the exponent. So what was our process? Multiply by the exponent, and then subtract 1 from the exponent. Let's do our process exactly backwards. So exactly backwards would be this step first, add 1 to the exponent, this step next, divide by the exponent. So here's what that looks like. add 1 to the exponent, divide by the new exponent. Of course, we always have a constant of integration plus c. So for example, I'm doing the antiderivative of x to the 8th with respect to x. I add 1 to the exponent, divide by the new exponent, plus a constant of integration. I've done the antiderivative. Then we can use our sum and difference rule just like taking derivatives. So we can split up and say the antiderivative of f of x plus or minus the antiderivative of g of x and do those separately. Then we have our 6 trig functions. We know their derivatives, so we can know that the antiderivatives of their derivatives lead us back to the function. Is that a tongue twister or what? So we think to ourselves, what function has a derivative of cosine of x? Sine of x does, but there could have been a constant there, so plus c. Cosine's derivative is negative sine, so if there's no negative in the integrand, we put the negative in the antiderivative. Secant squared came from tangent of x, possibly plus a constant. The cos are all negative derivatives, so if the integrand is not negative, the function antiderivative will be negative, and so on and so forth. You have to have memorized these derivatives to know these antiderivatives. Let's do a few examples. Find the antiderivative or the indefinite integral, check the result by differentiation. So I'm just going to split these up and think of them as one at a time since I'm adding and subtracting. So I have a constant multiple, so I'm just going to let the 5 hang out while I deal with the power rule for right here. Add 1 to the new exponent, divide by the exponent. Next one, let my coefficient hang out while I deal with the power rule right here. Add 1 to the exponent, divide by the new exponent. And then I have my constant right here, which had to have an x next to it to get 1, and then I always say plus a constant. So I simplify a little bit, clean it up, x to the 5th plus 2x cubed minus x plus c. Yay! Sometimes you're going to have to rewrite it, like x to the 4/3 plus 2 secant x tangent x. If we rewrite it, don't forget the dx, don't forget the integral, so it doesn't look like we've already taken the antiderivative. So follow our rule. Add 1 to the exponent makes 7/3. Dividing by the new exponent looks like that, but that's yucky, so multiply by the reciprocal instead. Plus 2 times, what's the function whose derivative is secant tangent? It is secant of x. Don't forget the constant of integration, plus c. P.S. Ask me to tell you an awesome joke in class. This is another one where we have to rewrite it. We cannot do the antiderivative of a quotient like we can't do the derivative of a quotient without a special rule. So we're going to distribute this division into all 3 of those. Rewrite this as x to the negative 2 plus 2x to the negative 3 minus 3x to the negative 4. Now we'll use our power rule. Add 1 to the exponent makes negative 1, divide by the new exponent. Let the 2 hang out. Add 1 to the exponent, negative 2, divide by the new exponent. Next one, let the 3 hang out. Add 1 to the exponent, divide by the new exponent. Don't forget the constant of integration. Rewrite negative 1 over x minus 1 over x squared plus 1 over x cubed plus c. Get a common denominator to clean it up a little more, and you can make it pretty. Or leave it like this. We clean it up a little, we get x squared minus x plus 1 over x cubed plus c. Both are good. Sometimes the directions will say, find a general solution to the differential equation. That doesn't mean anything different. It says find a general solution. That means solve. Solve the differential equation. Solve means make the derivative go away. So to make the derivative go away, we do the antiderivative. First, let's multiply by dx. So it looks like this. dy equals x to the 5th dx. Now we want the derivative to go away, so we do the antiderivative on both sides. This side will be y, the antiderivative of the derivative of y. This side, we use our power rule, add 1 to the exponent, divide by the new exponent, put a constant, done, general solution. Same deal here, rewrite it so the dt multiplies over here, 8t cubed plus 5 dt, and then do our antiderivative. Antiderivative. Antiderivative here is y. Antiderivative here, let the 8 hang out while we do t to the 4th over 4, add 1 to the exponent, divide by the new exponent, plus 5t plus c. Clean it up, y equals 2t to the 4th plus 5t plus c. Finally, just a couple different ways to see the variables. Dr equals pi cosine of theta plus 9 d theta. Do the antiderivative of dr, the antiderivative of pi cosine of theta plus 9 d theta. And the antiderivative of the derivative of r is r. The antiderivative of pi, a constant multiple. The antiderivative of cosine theta is sine of theta. The antiderivative of 9 is 9 theta. And I almost didn't leave room for a constant. Don't forget that guy.